In this video, I will be deriving a cubic polynomial from our cubic equation of state. Right? So we have P equals RT over V minus B minus A over V plus epsilon V multiplied by V plus sigma V. Right? And the first thing I want to do is I want to rewrite this in terms of compressibility. That's because when we implement this into code, we want a good initial guess. And for our compressibility factor, we know that it's going to be between 3/8 and about 1, right? So I'm going to write in Z equals PV over RT. So now looking at this left side, we already have pressure. So if we multiply by V over RT, we have compressibility on the left. So Z equals, and now we have to multiply by V over RT for both of these. V over V minus B minus A over AV over RT times V plus epsilon V, V plus sigma V, right? And now I'm going to do a little bit of simplification. From each of these right here, we can pull out a V term, right? And so I will go ahead and simplify. So Z equals 1 over 1 minus V over V minus AV over RT, RT multiplied by V squared multiplied by 1 plus epsilon V over V multiplied by 1 plus sigma V over V. Okay. And now we can see this volume on the top cancels out with one of the volumes on the bottom. And now I'm going to write in Z, or a term with Z for each of these volumes, because we don't know the volume. So when we use the cubic polynomial, we want to have all variables that we know, right? So we want to replace volume, and we know volume, right? We have this Z equals PV over RT multiplied by RT over P. We get that volume equals RTZ over P. And now I will go ahead and replace each of those in that equation right there. So Z equals 1 over 1 minus BP over RTZ BP minus A, right? We have this volume here. So AP over R squared, T squared, Z, right? Multiplied by 1 plus epsilon BP over RTZ multiplied by 1 plus sigma BP over RTZ. Right. Now we can see this, it's a bit of a mess, right? We've got a lot of variables, but we can also see these variables repeat in the same pattern, right? So we have BP over RT. Again, BP over RT, BP over RT. So I'm going to write in a variable, beta, which is equal to that BP over RT, right? And that'll make it a lot simpler, a lot easier to work with. And, all right, so we have 1 over 1 minus BP over RTZ. That becomes 1 over 1 minus beta over Z minus A. And if we write in beta here, right, we will have A, A beta times B over RTZ, or sorry, A beta over BRTZ multiplied by 1 plus beta epsilon beta over Z multiplied by 1 plus sigma beta over Z. Right. So now we still have the A over BRT, right? It's still a little too much. So we want to replace those again with Q. So Q equals our A over BRT, right? And that makes this equation look very simple, right? So we will have Z equals 1 over 1 minus beta over Z minus Q beta over 1 plus epsilon beta over Z multiplied by 1 plus sigma beta over Z, right? So now, moving from here, right, if we look, we have a Z term, right, and we have Z's on the bottom here. Oh, sorry, I missed the Z, right? If we divide by Z, that means we will have 1, we will multiply each denominator by Z. And that means on this second term right here, we will have Z squared, that we can distribute 1Z into each of these. All right, so I'm going to erase that here. So we have Z over Z equals 1. So 1 equals Z minus beta minus Q beta over Z squared, right? So we distribute both of those Z's. So we have Z plus epsilon beta times Z plus sigma beta. Now I'm actually going to multiply these two terms together now, right? So we have Z times Z. So that is Z squared plus Z times sigma beta plus Z times epsilon beta plus epsilon sigma beta squared. Right? So this is those two terms multiplied together. And now we can, if we want to combine these two terms, right, we can multiply by a common denominator. So, or to simplify these two terms, right? So we have this multiplied by Z minus beta, and that is our common denominator. So we will multiply everything by that. So on the left side, we have Z minus beta multiplied by Z squared plus Z sigma beta plus Z epsilon beta plus epsilon sigma beta squared, right? And that is equal to this term Z squared plus Z sigma beta plus Z epsilon beta plus epsilon sigma beta squared, right? In this second term, that will cancel out, and we just have Q beta times Z minus beta. So we will write minus Q beta Z, and because it's a double negative, plus Q beta squared. All right. Now I'll erase this over here. And I'm actually going to make a table so that it looks a little bit nicer, right? So if we subtract this right side from both sides, we can have 0, and that is equal to this other side, right? So we'll have 0 on one side, and on the other side, we have some z cubed, right? Z squared, z, and 1, right? So we have z cubed, and then our a coefficient, right? So we'll have our b coefficient times z, and our c coefficient times 1, right? And look, so now we just have to write each of these coefficients in. We start here, multiplying these two together. We have z minus beta times z squared plus z sigma beta plus z epsilon beta plus epsilon sigma beta squared. Multiplying those, right? So z times z squared, 1z cubed, z times z sigma beta is a sigma beta in our z squared term. And we have z times z epsilon beta plus epsilon beta, and z times epsilon sigma beta squared. So in our z term, we have epsilon sigma beta squared. Right. Now multiplying by negative beta on each of those, we have negative beta times z squared, negative beta times z sigma beta, so minus sigma beta squared, negative beta times z epsilon beta, we have minus epsilon beta squared, and negative beta times epsilon sigma beta squared, we have negative epsilon sigma beta cubed, right? And now subtracting these next terms, right? So we have a negative z squared, minus 1, negative z sigma beta, negative z epsilon beta, right? And negative epsilon sigma beta squared. And now we have this last bit here. So minus q beta, we're subtracting that. So in our z, yes, our z term, we have plus q beta, and we have minus q beta squared in our c coefficient. Right. And so I will be using this table here to implement our cubic polynomial into code later in this video. Now I will be implementing the SRK, equation of state. The first thing I want to do is define a function. We'll call it equation of state ABES with inputs temperature and equation of state, which we will default to SRK. I'm calling it ABES because those are the 4 variables that we will be pulling out of this. And so if we look here, our first parameter, alpha, for van der Waals equation of state is 1. For the SRK equation of state, it's this long expression right here. So we will write that in 0.48 plus 1.574 times W minus 0.176 times W times W squared, and we will multiply that by 1 minus the square root of TR, and it is all squared. Right? So now we can see here, right? Oh, actually first we need to write in EOS in brackets over here, right? So that knows that it's going to pull the string value associated with EOS. So it knows if EOS is VDW, it will give us an alpha value of 1, and if it is SRK, it will compute this value right here. So we see we have two variables here that aren't defined, W and TR. TR is our reduced temperature, right, which is just equal to temperature over critical temperature. And W is the eccentric factor of water, which I have right here, is 0.348. And now we have all the variables, we can move on. So sigma, oh, I need to write alpha equals this. Okay, so sigma for VDW, it is 0. And for SRK, it is 1, right? And EOS. All right, so now I'm just going to copy this. It'll make it a little bit faster. All right, so we have epsilon. For epsilon, both of these are 0. I'm still going to leave it in because if we implement this PR equation of state down here, then we can just add that on. It's a lot easier to implement more equation of states later on. Next we have omega. Omega for VDW is 1/8, and for SRK is 0.42748. And our final parameter, psi, for VDW, for van der Waals, it is 27/64. For SRK is 0.4274. Omega for SRK is not that. It is 0.08664. Yeah. All right. So now we're actually going to compute our A and B variables, right? So A equals psi times alpha times R squared times the critical temperature squared over critical pressure. You can see that down here. And B up there, right, is omega times R times critical temperature over critical pressure, right? And we want to return A, B, E, and S. Okay. So now I actually want to write in this equation of this cubic equation of state right here. So I will define it function cubic P, right? Because we are finding the pressure using a cubic equation of state. It has inputs of volume, temperature, and EOS, which again we will default to SRK. And the first thing we need is to pull these A, B, E, and S values. Right, so we'll say A, B, E, S equal EOS, A, B, E, S, using our temperature in an equation of state. And now we want to return this same function, right? Because we wrote this equation of state in for the van der Waals, right? And we can just copy that over to our cubic. All right, for our more generalized form. So now we can actually check to make sure that it is all working properly. I'm going to use 1 times 10 to the negative third meters cubed and 600 Kelvin for each of these. So cubic P, we will do the same thing. And we will specify the van der Waals. And we do get the same answer, right? And if we take away this van der Waals, we can see we also got an answer for EOS, or for the SRK, which is the default, right? So it is working, right? And we can see this, the SRK estimation is about 90,000 pascals lower, maybe like 87,000 pascals, but it is more accurate than the van der Waals. So that is what we will be using in general. Right, so moving on, I actually want to plot this SRK.
So I will just replace this van der Waals P with cubic P, right? And as soon as this loads, all right, you can see it looks about the same, right? But it's a little bit more spread out. Let's see here if I can, no, yeah. So comparing like, this one looks a lot tighter, right? Whereas this one, each temperature is a little bit more spread out as we get lower, and as we get higher, they're much closer together. Right. So moving on, right? The next thing I'm going to do is create a cube root, a roots function for our cubic equations, right? So I will define this as cubic roots. It has inputs A, B, and C. Those are our coefficients, right? You can see here. The first thing we need to do is compute Q and R. So Q equals A squared minus 3 times B over 9, and R equals 2 times A cubed minus 9 times A times B plus 27 times C all over 54. All right. Now, if R squared is less than Q cubed, right? So if R squared is less than Q cubed, we want to, that means we have 3 real roots, and we want to compute theta right here. So theta equals b dot arc cosine of R over p dot square root of Q cubed. And next, we can actually just, we can take our 3 roots we see in here, right? So if we return, we will return an array, right? So we have -2 times the square root of Q times the cosine of an array, and that array is our theta over 3, theta minus 2 pi, 2 times np dot pi over 3, and theta plus 2 pi over 3. All right. And then we have it all minus a over 3. Right. So here, in this document here, we have x2 is theta plus 2 pi and x3 is theta minus 2 pi. I changed that. I flipped them around. I do need to. There we go. All right. I flipped those around because the theta minus 2 pi over 3 will actually be the intermediate value, and the theta plus 2 pi over 3 will be the largest value, right? So now we have our else function, right? Because if r squared is not less than q cubed, we want to compute capital A, right? And that's equal to the negative of r plus the square root of r squared minus q cubed, all to the power of 1/3. Now what I'm going to do here is I'm going to make a separate variable for 1/3. So we'll write 1/3 equals 1/3. That's so that when I compute this, right, when I run the code, I should say, anytime I use the function, instead of having to compute 1/3 every time, it has a separate variable for that. So next we have B. So B equals, we can see b equals 0 if a is equal to 0. And it is equal to q over a any other time, right? Because if we had it always equal to q over a, when a is 0, that wouldn't work because it would be infinity, right? So now we just want to return our one real root. So a plus b minus a over 3, right? And that should be good. Oh, if a is equivalent to 0. Yeah, we want to do a check, right? We don't want to assign a to 0, right? Or 0 to a. Okay, so now I don't need that anymore. So we're going to check these, right? So if I'm going to zoom in here. We'll go with 600 Kelvin, right? And if I zoom in here, we can see if we were to have a pressure, right, a given pressure, we'll say 10 million pascals, we draw a line across, we can see that it intersects this volume curve 3 times, right? That's our volume of liquid, intermediate volume, and volume of vapor, right? So first I'm going to check, right, to make sure these cubic roots are right. So if I did np.polynomial from roots, I said 1, 2, and minus 5, right? I need to put these in brackets here. All right, so we have an equation here. If we put in our cubic roots function, right? So a is 2, b is minus 13, and c is 10. We have an issue here. It takes from 1 to 2, but was given. Oh, do I need to put these in brackets here? I believe I do. Yes. Okay. So we did get our roots back, and they are in ascending order. Okay. So now going back to this, right? If we were to draw a pressure line across, it intersects this curve 3 times, right? And we want to find those 3 points, those 3 volumes, right? So if I define a function, we call it cubic volume, right? With inputs of temperature, pressure, and our equation of state, which we default as SRK. And we want to pull our A, B, and S values right here. All right. So now I'm going to use this cubic equation right here. I have all the coefficients listed out. This is what I computed on the board previously, right? But first we need to write in Q. So Q equals A over B times RT. Q equals A over B times R times T. And beta, our other one, right? We have beta equals B times P over RT. B times P over R times T. Right? And now we can write in phi there. Okay, now I can write in each coefficient. So we have, we want our z's, right? Because this is for, we have a z value, right? So these equal cubic roots, underscore here, and I'm just going to write in each of these coefficients. So the first one, we have E plus S times beta minus beta minus 1. The B coefficient is E times sigma times beta squared minus E plus sigma times beta squared minus E plus sigma times beta plus Q times beta, right? And for our third one here, we have minus E times sigma times beta cubed minus epsilon, not just E, so minus epsilon times sigma times beta squared minus Q times beta squared. All right. And now we want to return our volumes, right? So we said that volume was equal to Z times R times T over P. So we can return Z's times R times T over P. And unmatched parenthesis. There we go. Okay. So now if we look at this, right, we can go with 10 million pascals and 600 Kelvin. So if we do cubic V of 600 Kelvin and 1E7 and default to SRK. All right, we have our three values here, right? This one is about 42 micrometers cubed. Excuse me. And we can see that matches, right? This one is about 80 and it matches again. And then we have about 377, right? And all the way over here, you can see it once again matches. So we can say these cubic roots function, sorry, not function, what we've done here is correct. Okay, so now we are going to do the Maxwell areas construction. Right, and so what that is when I take this line across 10 million pascals, right, if I integrate this area here, that is our first area, and our second area is above this line. And the Maxwell areas construction says that when these two areas are equal, that is the pressure that is the vapor pressure of the vapor at the given temperature, right? So given a temperature, there will be one pressure value where this area, this bottom area, and this upper area are equal, and that is the saturated vapor pressure. Right? So let's define this function. So define Maxwell areas, right? Given a temperature, a pressure, and an equation of state. So like I said, the volumes, right? So this first one is our liquid, our volume of the liquid. This second one is an intermediate, and this third is vapor. So we will write that in. VL, VM, and VG equals cubic roots, or sorry, not cubic roots, cubic V at the temperature, pressure, and EOS. And now what we are going to do to integrate is use quadrature. So if we go up to the top here, from scipy.optimize, import quad. Right, now we have the quadrature integration function. not function. It is a function. The quadrature integration, right? We can integrate these areas. So we want to return the value of the quad, and our lambda is v, right? That's our integration or variable of integration. And this first one, the pressure is higher than the equation of state. So we will have P minus cubic P of the temperature, pressure, or sorry, of the volume, temperature, and equation of state given. And we want to integrate from the liquid to the intermediate, right? And then I'm going to copy this. For the second area, we are integrating from the intermediate to the vapor, and the pressure will be lower than the equation of state value, right? So we're going to subtract that. Now, I do want to check. Oh, not SciPy to optimize, SciPy dot integrate import quad. Did I get these? Volume, temperature, EOS. Volume, temperature, EOS. Okay. Okay. So now we have our Maxwell area, and if we go ahead and put in our 600 Kelvin, 10 million pascals, and we won't write in the EOS, right? Okay. So now we have two sets of numbers. This second number right here, this very small one, that is our estimated error, right? We're not worried about that right now. So we are going to write in after each of these. We want just we want just the first value, so we'll write in brackets 0. So now we can see 152 and 869. So 152 is the area of this section right here, and 869 is the area over here. And now I'm actually going to use this Maxwell area function to estimate the vapor pressure of water at 373 Kelvin. Right, so at 373, if we said about atmospheric pressure, right, we can see it is pretty close, but we can get a little closer. We'll try 95,000. Oh, not close. 90,000. Something isn't right here. Or sorry, you know what it was? I did 950,000, didn't I? Yeah, okay. Not 95,000, so 95E3. Okay, so it is getting closer. And okay, so 90,000 just about. Maybe we could get a little closer. All right, 91,000. So this Maxwell area's construction right here is essentially saying that at 373 Kelvin, it can estimate that the vapor pressure of water is 91,000 pascals. And thank you.